Okay, thanks a lot. So good morning, everyone. Hope you had a great first day. So who of you did work on the tutorials after dinner yesterday? I see one hand, second hand. Okay, so this is about average expectation I had. 2 people out of around 30, this is okay. So for the others, you can still try to look at the problems, especially if you ever have to solve QCD beta function. I recommend. Of course, you can program it by yourself, but I recommend that you also take a look at packages where people have implemented this already, and then you have a cross-check on the numbers that you get. Right, yeah, so the sheets are on Indico. Right, and then the question is, I briefly wanted to ask you, so there is this question, what are the limits on the meta content of QCD in order to maintain an asymptotically free gauge theory? And what is the value of NF for the conformal fixed point? So anyone has thought about this? So if not, I tested this question also on ChatGPT yesterday, just to get an idea on the quality of the answer, and it actually gave the right answer. So basically, for the theory to be asymptotically free, you have to have a negative beta function, because otherwise the coupling would grow in the ultraviolet, and this is not what we want to have. And so for the beta function to remain to be negative, you have to look at leading order, you have to look at the beta naught coefficient here, which is 11 over 3 times NC minus 2 times NF. So in QCD, NC is 3. So actually ChatGPT knew this without me telling it. So this is 11 minus 2 times NF. So in order for that number to remain positive, so that the overall sign here remains negative here, you can solve it easily for NF, and this will give you then 11 by 2. So 33 over 2. So NF has to be smaller than 33 over 2. Means you can have QCD with up to 16 different quark species at leading order, and it'll still be asymptotically free. Of course, if you go to higher orders, the beta function will change, and this computation has to be redone, and then the window narrows a little bit. And the other question is the conformal fixed point. So we think of a conformal theory to have the property of being scale invariant. Now, if a theory is scale invariant, means the beta function is vanishing. So at least at leading order, you have to search for the solution for this coefficient to vanish. And this you can also see quickly then by solving this equation. So this is just for you to keep in mind. Okay, but if you have further questions, I'm happy to chat about this with you. Let's start. So today I would like to talk about QCD at work, and the keywords are infrared safety and jets. We had already yesterday a great lecture, first lecture on jets by Sanmoy, and I will cover parts of the things that he said again from a different angle. So my approach to QCD is basically, it is the gauge theory of the strong interactions. And as such, it covers the dynamics on a very large range of scales, from basically hadron scales all the way up to high energy scales at the LHC. And it is essentially established. So it's not, we don't test QCD anymore. So maybe 20, 30 years back, experimentalists wrote papers about testing QCD, but nowadays we don't test QCD anymore. So we basically take it as an established part of our toolkit, and then we work with it in order to discover new physics phenomena or to have better explanations of whatever measurements are being made. Yeah? So in this sense, we try to understand QCD to the best possible, in the best possible manner, and then we try to use this and get the best possible description of our data based on this. And if then at the end of this process there are still deviations or discrepancies, then we have a better ground to argue for any deviations of our searches for physics beyond the standard model. And if you want to use QCD at a collider, there are actually not so many things that you have to know. There are a few basic keywords. First one is infrared safety, second is factorization, and the third is evolution. And if you grasp the underlying physics, then I think you're good to go, and you're ready to do LHC phenomenology. So today I'd like to talk about infrared safety, and that means that when we take QCD, you take textbook QCD and you try to apply it, then you can only calculate a very small number of cross-sections actually directly in perturbation theory. And this small class, these are infrared safe quantities which are free of any long-range dependence, at least at the leading power in some large momentum. And for those quantities, the general structure of the cross-section is that we have some cross-section. It depends on some large momentum scale and our renormalization scale, and we can compute it directly in a power series in the strong coupling with finite coefficients which only depend on this hard scale and the renormalization scale. And typically, as a dimensionless ratio, we put it as Q over mu. And the examples I have in mind are total cross-sections in E plus E minus annihilation. For instance, so if you take E plus E minus, they annihilate, and then you produce hadrons, and you basically measure 4 pi, you measure all the hadrons that are coming out totally inclusively. You can still normalize it to the cross-section of E plus E minus going to mu plus mu minus. Then you have a dimensionless number, and this is a quantity that you can calculate directly in QCD. And this is infrared finite. Then also some cross-sections in E plus E minus annihilation. You can do the total width of the Z boson, you can calculate, and these are finite quantities that we can do directly with perturbative QCD. Okay, so in order to illustrate this, I would basically like to do this calculation here with you at the leading order and the next to leading order, that we see what goes into it and how the different ingredients then add up so that we get a finite cross-section. So at leading order, this is really very easy. E plus E minus going to hadrons. This is just the QQ bar pair in the final state, mediated by a photon here. And this is just one diagram here. You write it down, the Feynman rules. You square the amplitude, and then you get 4 pi times alpha electromagnetic over 3 times the center of mass energy. So this is the number. This is fine. And then we want to add QCD corrections. So since we only have colored particles in the final state, we arrive at the same diagrams that were already discussed yesterday in the last lecture in full glory. But since it's an important process to illustrate a few key concepts, I'll walk you again through a little bit different notation. So what I would like to do is I would like to consider those amplitudes in dimensional regularization. So I work in 4 minus 2 epsilon dimensions here, and I write down the two diagrams here with a gluon emission from the Q bar and a gluon emission from the Q line here. I add them up, square them, and then I evaluate the squared matrix element, and I do the phase space integration. And if you write this down, then typically you would be starting with scalar products of the associated momenta here, and you integrate over some of the angles of the phase space. And in the end, you can express everything in a compact form as a two-dimensional integral, where you write this squared amplitude and the phase space integration in terms of the scaled energies of the outgoing quark and the anti-quark here. So I denote them by x1 and x2. So x1 is 2 times the energy of the quark divided by the square root of the center of mass energy. And x2 is 2 times the energy of the outgoing antiquark divided by the square root of the center of mass energy. And in terms of these two variables, x1 and x2, so these rescaled quark energies, the matrix element squared in d dimensions takes a very simple form. So I simply have x1 squared plus x2 squared, and then I have a 1 over 1 minus x1 and a 1 minus x2 in the denominator. No? And then because I work in d dimensions, I have from the traces of the Dirac matrices, I have some term which is epsilon dependent here. So that would be absent in 4 dimensions, but I have to keep it in d dimensions. So this is 2 minus x1 minus x2. And then in the denominator, those terms, those factors 1 minus x1 and 1 minus x2, they don't come with unit power, but they come with the power 1 plus epsilon. And now you see already why it is nice to work in d dimensions, because if I then do the phase space integration in the variables that I've chosen, namely x1 and x2, then the phase space runs in those variables between 0 and 1. Now 0 is not a problem, but 1 is a problem, because if x1 goes to 1 here, then you see I have a divergence in the expression. And working in d dimensions helps me to regularize this divergence. So in this sense, I'm using here dimensional regularization to regularize divergences which appear here from phase space emission. This is not a UV divergence here.
Diagram, one would think that one doesn't have to.
Right, it's not a UV divergence. So the type of divergence we are encountering here, this is the divergences we are encountering here. These are soft and collinear divergences, because if you go back, what we really have here is we have the emission of a gluon from a quark line, and then we are parameterizing the quark energy as x1, and if we can write down, since we have energy momentum conservation, we can write down this 1 minus x1 also as the energy of the antiquark, so the x2 variable, times the gluon energy divided by the center of mass energy, and then we take the opening angle, 1 minus the cosine of the opening angle of the emission of the gluon and the antiquark. So in terms of those variables, so now we parameterize everything in terms of the gluon energy and the cosine of the angle between the gluon emission and one of the gluon emitted and one of the quark lines. You directly see the nature of the singularity, because you see now that 1 minus x can vanish when the gluon energy becomes soft, so when the gluon has vanishing energy. So this is the soft singularity which is hidden there in this expression. And the other singularity is collinear, namely when the 1 minus cosine theta vanishes. This is the collinear singularity. Yeah? And likewise, we can do it for the 1 minus x2 singularity that we had there. We can also rewrite that one in terms of the rescaled quark energy, the gluon energy rescaled, and 1 minus the cosine of the angle between the gluon and the quark. So we have in those two expressions here, we have in each of them we have a soft singularity when the gluon is vanishing energy, and we have a collinear singularity depending on whether the quark becomes collinear, the gluon becomes collinear to the quark or the antiquark here. So we use here dimensional regularization to regulate infrared singularities. This is the important thing, and this is also why dimensional regularization is really used broadly in computations, because it's so versatile. We don't really have to care whether it's ultraviolet or infrared. We just have a good regulator. Huh?
Excuse me. So in this parameterization, like how do I know that gluon is being soft? Like
How I know whether the gluon is soft?
gluon is soft. So in this parameterization, the x1 and x2 like can be soft depending upon the quark and anti-quark energy. But how do I know that gluon is become soft? Like
But when the gluon is soft, when the gluon energy is vanishing. Huh?
yeah, in this
I mean,
parameterization, how do I recognize that?
I have different ways of doing the phase space, you know. So basically, when I do the integration here, I have to integrate over the form momentum of the gluon, and there are different ways I can do this. So one way of doing the phase space is I can integrate out the angles, and then I parameterize everything in terms of the rescaled quark energies. But I can equally rewrite the phase space here and parameterize it in an integral over the gluon energy and over the angle, over the azimuthal angle or the polar angle for the emission of the gluon relative to the quark or anti-quark. So this is freedom that I have in doing parameterizing the phase space. And for computational efficiency, this is the easiest because in this way I just have a polynomial over x1 and x2 and I can simply integrate. But in terms of explaining the physics, the underlying physics, it's more advantageous to talk to you in terms of gluon energies and the angles that are involved. We'll come back to that later, again in a different formulation. So it's good to look at it from all sides.
And next question is that, like in the last slide, you have introduced some large momentum, some Q, and in this NLO amplitude, how can I see that large momentum scale in the cross section?
So Q is any large momentum scale, and here for our scattering, this is basically center of mass energy. So this is the large scale in the problem.
Let's say for the PP collider, so for event by event, that will be S hat, and let's say for the low energy scattering, that is not a large momentum scale.
I consider this process now at a fixed value of the center of mass energy, and this I take large. So in order for QCD perturbation theory to make sense, we have to look at this process at scales of at least a few GeV. So we have to think of this, we have to be above all the meson resonances. So think of center of mass energy to be at least 2 GeV. It can also be 100 GeV, I'm fine, but think of it as at least being 2 GeV. Okay?
Okay.
Dimensional regularization, but let's say when people try to address UV divergence, there are many regularization schemes. So I was just wondering if, apart from dim-reg, there are other regularization schemes to tackle the infrared divergence.
Oh, sure. I mean, there are many. So basically, we can also simply make cuts on the phase space. Like in the ultraviolet, when we go to the ultraviolet, the toy regularization is always we put a lambda cutoff in the ultraviolet, and we work with this. And likewise, in the infrared, we basically put a low cutoff at the small relevant momentum. And
that's almost like a Pauli-Villars kind of thing.
No, this is then not Pauli-Villars. So we basically would then, if we want to have regularization schemes for the infrared, so for soft and collinear singularities that work in 4 dimensions, then we would basically make a cut, for instance, on the transverse momentum of the emitted particle. And this then goes under the name of QT slicing. And this is implemented also in parton level Monte Carlo generators that do next to leading order computation. So at NLO, we are pretty happy with dimensional regularization because this is also at the core of Catani-Seymour dipole subtraction. But then at next to leading order, we are still developing different ways. And in one of the schemes that is being applied is QT slicing, and it is entirely four-dimensional, and you basically make a cut in phase space. Yeah.
So related to his comment, like there are mass regularization. So you introduce some small mass, photon mass or some gluon mass, and then your all divergence comes. I mean, appear like a logarithm of that mass by some high scale. So mass regularization is also there for the infinite.
Yeah. Okay. But we don't. We don't really like to work with I mean, photon mass you can do. This is one thing that you do in textbooks, but we don't really like to work with a gluon mass, for instance, in QCD. So this is not really done. Partly also because then it breaks gauge invariance, and so this is not really commonly used. Yes, yeah. So
loops have to be. So I'm just trying to understand what regularization to choose to kill this one. So
Right.
that loop diagram, whatever regularization I should use, I must use the same here.
I followed the discussion yesterday, and I thought maybe this is a simple example that will and you're ready to bear with me for 2 more slides, because I think you can do that integral here easily in terms of the Euler beta function, yeah, because you just have x1 to some power, you have 1 minus x to some power, you integrate over x1 from 0 to 1, so this is giving you just a bunch of gamma functions, yeah. So you do the x1 integral, and the x2 integral also gives you a bunch of gamma functions, and they only depend on the powers of the denominators here and the numerators. And then you expand these gamma functions in epsilon, and since there is a divergence, there will be poles in the gamma function. And if you do this now, we integrate over the phase space, we do this, we expand those gamma functions in epsilon. This is the expression we get. So this is something that, this is directly the previous, this equation integrated over x1 and x2, and then expanding the gamma functions in epsilon. So we get a divergent result. I put here some f of epsilon. This is just some residual dependence on epsilon. It doesn't matter, so I've extracted all the poles here. Yeah? And I expanded up to the finite piece. I killed all the epsilon terms here. But we see we have a double pole, 2 over epsilon squared. And this is basically when we have a soft n collinear singularity, both at the same point. And then we have 3 over epsilon. This is the collinear singularity. And then we have a finite piece. But of course, this is not a sensible cross-section which we can give to our experimental friends. So there has to be more. And those divergences now have to be cancelled by virtual contributions, which come in at the same order of alpha s. So if you do your counting of the coupling constant, then you have 1 power of gs here from the squared amplitude. You have another power of gs. So altogether, this gives you 1 power of alpha s for the squared amplitude. Yeah. Now you go to the virtual diagrams. And so the one loop virtual diagram has gs times gs. This is power of alpha s. And then you have to square this with the Born contribution, which has no alpha s. So this times the Born comes in at the same order of alpha s. Now we have to do this loop diagram here. And we have to do this loop diagram. It's a simple one loop diagram. And if we do this, then we see I've normalized so that everything is the same as in the real emission case. So we can factor out the Born cross section, we can factor out a factor 3, we can factor out the sum of all quark charges, this epsilon function, we can also factor out color factor and alpha s over 2 pi, we can also factor out, and then the whole remnant of this loop integral is basically minus 2 over epsilon squared minus 3 over epsilon minus 8. So this is what we get from this diagram alone. And again, this pole here, 1 over epsilon squared pole, this is when this gluon, which we exchange here, is becoming soft and collinear. So it's the same underlying physics. Yeah? It's just a virtual contribution, and we integrate over all gluon momenta here in this loop, but the singularity is of the same origin, namely when that gluon here is soft and collinear to any of these quark momenta in the loop, outgoing quark momenta. So this is what is happening there. And then we also have the self-energy corrections here. So we have a gluon emission on each of the outgoing quark lines. And here the nice thing about dimensional regularization is that in dimensional regularization, those are integrals without any scale. You can write them down, but since the outgoing quarks are all on shell, then you have integrals without any scale. And if you go through the math in detail, then you will see that those integrals have an ultraviolet pole and an infrared pole, and in dimensional regularization they precisely cancel. So these are scaleless integrals, as we call them, and we simply eliminate. We can simply drop them in dimensional regularization. So this is also one aspect why we use DIMREG, because we can directly eliminate a couple of diagrams. Yeah? So this wouldn't be the case if this was a massive diagram, because if this was a massive diagram, then this would at least contribute to the mass renormalization, but since we have massless quarks, it simply vanishes here. So now we have these two results here, and in order to compute a total cross-section, now we simply have to sum up all contributions at a given number of at a given order in perturbation theory. So since we're working at next to leading order, we sum up all the contributions which are proportional to 1 power of alpha s. So we have the real emission part, which is the first line. We add the virtual contributions, and then we see that all these pole terms precisely cancel, and we end up with a finite result, which is in the normalization that I've chosen is simply 3/2. And then we can then finally go back to our example. We can compute the ratio, the R ratio, so the hadronic cross-section normalized to the cross-section of E plus E minus to mu plus mu minus. That means basically we'll be dividing by sigma naught everywhere. And then we look at the end, we add the Born term as well. So finally we get 3 times the sum of all quark charges, and then 1 is the Born result, and then the NLO result in the end, if we apply it to QCD, meaning we take CF to be 4/3. So this is 4/3 times 3/4, so we end up with a factor alpha s over pi. And this is the whole NLO correction to the R ratio. And this is finite, and this is simply a number which we can compute. Okay, so this is a nice example in DIMREG. This is looking at the same physics that were discussed yesterday, already from a different perspective. Unfortunately, or I should say first, this type of physics also happens in other processes. So I have now discussed with you E plus E minus to QQ bar pair with 1 gluon emission. I can look at other basic QCD processes. So for instance, I can look at the Drell-Yan process, which is basically the reversed process. So we have QQ bar annihilation, and then we have, say, mu plus mu minus pair in the final state, and then I have gluon emission from the initial state. Or I can look at deep inelastic scattering, where I put this process here in the T channel, and the photon exchange in the T channel, and I have the electron scattering of a quark, and then I have gluon emission either from the initial or the final state quark. So basically the same type of physics that those collinear singularities, they also appear in other types of processes. Unfortunately, when I consider those other type of processes, then I have to apply more machinery in order to arrive at finite results, because I cannot get a finite result simply from doing those computations alone. And this goes under the name of factorization, and this is the topic that we'll discuss then tomorrow. So, but for the small class of processes, say E plus E minus related observables, we'll basically be having a finite result. Yeah. Now, staying with this process, I would briefly like to talk about jets in QCD from a theory perspective. So we had already a nice introduction to jets, and we saw, yesterday we saw modern jet events from the LHC event display. So this is an old three-jet event in E+E- from the OPAL collaboration, which ran at the Lab Collider at CERN more than 20 years ago. And so you see you basically have E+E- annihilation, and then here you have three jets like quark, antiquark, and you have a gluon. So this would be basically coming from something like this. Yeah? And of course, jets are related to the underlying QCD dynamics. And experimentalists like jets because you see the final state here is rather complex. And if they identify all those particles as one jet, all those particles as one jet, and all those particles here as one jet, then it reduces the complexity of the final state. So this is the main idea of talking about jets, that you don't have to look at the individual hadrons, you just look at some stream of hadrons in some part of your detector and then cluster them all together. Yeah? So it reduces complexity, and it also connects the parton picture that we have to some experimental signature, because we can basically make our parton computation. We have to hadronize, of course, at some point, but pretty much it connects the partons to the experimentally observed streams of hadrons. What we have to do, and what is a challenge for the theorists, is that we have to do our particle form momenta that we use in our computation. So when we have a diagram like this, we assign some particle form momenta here, and we do our phase space integrations. We have to assign those sets of momenta to jets momenta. Yeah? And this is the task of jet algorithms, and this is a delicate issue, so we can discuss this a little bit further. But by and large, properties of jet definition. So this was early on, already at the beginning of the 1990s, when people figured out that jets is a useful experimental concept. Then they came up with a set of rules, which I think still hold today. There should be definition of a jet should be simple to implement in experimental analysis, but it should also be simple to implement in a theoretical calculation. Yeah, because in the end we have to deliver to the experimentalists, and if we have an observable which we cannot calculate, then there is no way to move forward. They should also be defined at any order in perturbation theory, and they should yield finite cross-sections at any order in perturbation theory. And this is an important thing, and this is why I'm discussing it now, because we have to come up with definitions of jets which are also infrared safe. Yeah? And in the end, it should also give you cross-sections that are relatively insensitive to hadronization. Yeah? So after all, the conversion from partons to hadrons shouldn't really spoil or give you big corrections to your cross-sections. In reality, it does give corrections, and those have to be studied with Monte Carlos, and Monte Carlo tunes, but I would like to minimize this. Huh? And the historical definitions of jets, I think the first one was due to Sturman and Weinberg. They came up with a criterion for a two-jet event, where they simply said, okay, let's talk about a two-jet event. If we see particles arranged or clustered in two cones back to back, and the cones should have an opening angle alpha, and we should see in those two cones, which we should see particles with a small fraction beta over 2 of the total center of mass energy in the event. Yeah? So you're basically asking a question. Okay, I have a center of mass energy of a collision, and then in the end, I look at two small cones in my detector back to back. And then I would like to see particles with a small energy fraction in cones with that opening angle. So this is the definition they came up with. It's a definition which is good for explaining certain features of of jets, but it was quickly realized that this is not really practical for multi-particle events, because then you need to define cones here and there and count the energy fraction. So this is why the Sturman-Weinberg jet criterion is basically something that has been applied for 2 jet events. Yeah? And then quickly afterwards, the so-called JADE algorithm was invented, which is then going a little bit in the direction of modern jet definitions. So basically, you define some jet by looking at particles or partons with momenta, and then you look at the sum of those momenta, and you put them into one jet or you put them into separate parts, so outside one jet. If the summed momenta are smaller or larger than some y-cut that you've introduced, so y-cut is again a small number, could be 0.1, 0.2, and you, of course, since this is momenta, you have to put them relative to some hard scale in your process, and you again take the center of mass energy S. Yeah? So then the jet definition algorithm would be you take the minimum of the momenta of particle I and particle j, you square it, sum it up. This you can rewrite in terms of the particle I energy, the particle j energy, and then the angle between them, the 1 minus cosine theta angle between them. And if this is larger than some y-cut, you would put it into separate, you would keep it as separate jets, and if this is smaller than y-cut, you basically say, okay, they're really close to each other, and so you would put them in one jet. So this is one way of putting things together. Huh? It has some, basically it's historical, because people then realized it also has some disadvantages, because depending on the phase space, it puts also soft gluons with a large relative KT into one jet together. So it's not really a good mapping of your phase space topology to the jet topology. But for historical purposes, I'd like to go through and discuss it with you. First thing we can do is we can take such a jet definition, and then we can look at the phase space which is available to you. So in terms of these, so we are basically looking back at this expression here. Yeah, so this is the expression that we have here for the one gluon emission and 2 quark lines here in terms of the scaled quark and gluon energies. Now we take it in 4 dimensions because we make cuts so that we don't run into the soft and collinear singularities. So we're basically looking at x1 squared plus x2 squared over 1 minus x1, 1 minus x2. So this is the phase space we're looking at. And in terms of x1 and x2, then this is the totally admissible phase space here, so it's the upper triangle here. And then with certain cuts on soft and collinear singularities. So for instance, taking the Sturman-Weinberg jet definition criterion with a beta of 0.3 and a delta of 30, and the delta is basically the tangents of alpha over 2. So having some definition of the cone, then this red area here, this is what is being covered then by the dijet phase space. Huh? So anything inside here, this is then an integrated dijet event, and you see that all the soft and collinear singularities here, they have been cut out. Huh? If you take instead a J-jet algorithm and you put a y-cut of 1, and you map the available phase space, then you get this blue dashed triangle here. Yeah? So you see, depending on the jet definition, you cover different areas of the phase space. It also means your cross-section is different, yeah? Because you're cutting away different parts. And it means that the algorithms that you choose for defining your jets, they alter the energy and momentum clustering, and those differences, they also affect the jet multiplicities observed. So I think this is something to keep in mind and this applies to all the jet algorithms. We can move on then with this example, and we can look at the ratio of the jet rates. So this is now for the jet algorithm. We can look at the values of y cut, and then at the relative rates where we identify an event to be either 2 jet or 3 jet. And then you see with a small y cut, basically everything is a 3 jet event, but it diverges because we're running into soft and collinear singularity. And there is no 2 jet events because even the softest gluon would be identified as 1 jet here. Yeah, but of course this divergence we have to cut off, and then as we increase the value of y cut, we see that the number of 3 jet events that pass actually our cut, this is going down. So if we have a y cut of 0.1, then only about 10% or so of all events would actually pass as a 3 jet event, while we would already say that 90% of our events would be classified as a 2 jet event. Yeah. So basically being inside or outside this triangle here. As we increase y cut, basically we kill the number of the 3 jet events. Yeah? And this is basically all coming from this simple expression here in terms of the rescaled quark and gluon energies. Right. So we can move on, and since I heard the discussion yesterday that you had in the last lecture about the theory concepts, and also about the notion about infrared finiteness, I thought we keep this example and we continue looking at it now from the viewpoint of the jet perspective. Yeah. So before we had integrated this in d dimensions. We had paired it with the virtual corrections, and we got a finite number for the total cross section. Now, if we just stay with this 3 jet cross section and we look at it from the jet perspective, then we can rewrite this actually again in terms of the different variables. So we can rewrite the expression, instead of taking the rescaled quark and anti-quark energies, we can rewrite it in terms of the gluon energy and the cosine of the quark and the gluon emission angle. And then if you do your math and if you translate x1 and x2 and 1 over 1 minus x1 and 1 over 1 minus x2 to the variables gluon energy, which if I rescale the gluon energy in the same way as the quark energies, I call this variable x3, and I take the cosine of small angles, then this whole expression stays a simple expression, so it becomes 2 over sine squared theta of the angle between quarks and gluons. And then I have 1 plus 1 minus x3 squared over x3 minus x3. So I have a simple polynomial then in the gluon energies. And then I can go to the small angle approximation, yeah, because we're interested in collinear singularities, which are happening at small angles. So then the phase space here, d cos theta, 2 times d cos theta over sine squared theta. This can be expanded for small angles in terms of the d theta over d theta squared over theta squared plus d theta of the q bar gluon over the theta squared of the q bar gluon. Yeah? So I can basically split this into 2 angular integrations, 1 angle quark to gluon and 1 angle quark to anti-quark to gluon. Yeah? And then you see here that the 1 over the d theta over theta and d theta over the theta q bar, this is the collinear singularity, and here the x3 in the denominator, this is the soft singularity. So we again have the singularities manifest. Now I'm writing it down in this way because what we are seeing here now is we're seeing now this this polynomial in x3 in the gluon energies, multiplying the collinear divergences. Yeah? And this polynomial is a well-known function in QCD because it is just the QQ bar, the QQ splitting function at leading order, which is 1 plus z squared over 1 minus z, evaluated now at 1 minus z, or 1 minus x3 I should have written here. Yeah? And so in this way I can rewrite the 3-jet cross-section basically as a differential, an integral over the angle, gluon emission from the quark line, and here I have to sum over the gluon emission from both the quark and the antiquark, and then the polynomial this is being multiplied with is the so-called splitting function, and this splitting function, this is a universal quantity because it captures the universal dynamics of collinear emissions in QCD. So this is this functional form here for the splitting function captures the full dynamics of at leading order of a gluon being emitted from a quark. Yeah? Or if you wish, you can also think of this as the quark going into a quark under the emission of a gluon. And this is universal, meaning it is process independent, because you find the same function in any collinear emission processes anywhere in QCD. Yeah? Whenever you have gluon emission from a quark line. And so here with our simple rewriting of the 3-jet cross-section, we can actually identify the QQ bar splitting function at leading order. Yeah? So this is one way of actually calculating it. If you've never calculated it, then this is one way of doing it. Right. The fact that we have rewritten our 3-jet cross-section, the collinear singularities, we've rewritten it as the sum of the differentials of the two angles, so gluon with respect to quark and gluon with respect to antiquark, also tells you that we simply sum over the gluon emissions individually. So this gluon emission happens individually from each of the quarks that we have in our process. Again, underlining the universality.
I would have got the same Z dependence, right?
Right.
CF will not be there, some other company.
Exactly. So this is entirely this is entirely related to all these particles here being massless, because you can if you went back, right. So if you look back at this process here, and you would be parametrizing, if you took a massive quark here, and you would be parametrizing then the momenta in the same way as I've done here, yeah, then you would be seeing that the mass of the heavy quark would basically put a small factor mass of the quark over the quark energy in front of the cosine here. And then since the quark mass is then 1 minus the quark, so it would be put the square root of 1 minus the quark mass over the quark energy in front here. So a factor unity if you have massless quarks, but a factor smaller than unity if you have massive quarks. And so the quark mass would actually screen the collinear singularity. Yeah? So the appearance of these splitting functions actually is entirely due to the fact that we have here massless emissions. Yeah? Okay. Right. So this is one thing we can learn from this. And I'll come back to the splitting functions tomorrow when we discuss more about factorization. So the other lesson that we learn here, that we have independent evolution of the emission of the two jets with the splitting functions. So we can take each quark line separately. And then we can also take the splitting function at small energy fractions. Yeah? So we have here the splitting function at 1 minus z. That means there will be a 1 over z denominator. And then if we write the differential 3-jet cross-section, differential in the z variable, then we have an easy way of coming back to the formula that was discussed yesterday for the Sudakov form factor. So we basically can approximate this expression, the jet rate in the case of small angles and small gluon energies, simply as a d theta over theta squared and a dz over z. And in this way, this is called Sudakov form factor. As a form factor, because you can resum it and exponentiate, but it's also entirely written in terms of four-dimensional variables, and this makes this form also very suitable to implement in Parton-Shaw Monte Carlos. So then you can take this as a proxy for gluon emission, at least to leading logarithmic accuracy, because here you have simplified everything that this is just accurate to the leading logarithm. But in this way, you can basically also model in Parton-Shaw, gluon emissions in Parton-Shaw. Yeah? So we've learned a lot from this simple example, looking at it in different ways. And I hope I could contribute a little bit more to the discussion that was already going on yesterday. So last comment I would want to make on this simple example is we can now go back to the Sturm and Weinberg cross-section. And we can basically take here our cross-section in whatever form we have it, either here as dx1, dx2, or we can take it in terms of cosine theta and the x3 variable, and we can integrate it over the whole phase space with a Sturm and Weinberg cut. So we can say, okay, we want to integrate it now such that we look at the two-jet rate for events which have a small fraction, energy fraction beta, in some small cone with a parameter delta. And then integrating this and dividing out the bond cross-section, you get a simple result at NLO. So 1 is the leading order number, because at leading order you always have two jets back to back, so normalized this is 1. And then the NLO correction, according to the Sturm and Weinberg jet definition, is giving you alpha s over 2 pi times Cf. And then you'll be getting minus 8 times the log of delta, which is, so delta is the cone, is the opening of the cone. So this is the collinear singularity. Then you have a log of beta. This is the energy fraction that you have. So beta becoming soft is a soft singularity here. So you have the log in delta and the log in beta, the collinear and the soft singularity again. And then you have minus 6 times the log of delta. This is again a collinear singularity. And then you have some finite constant which you have to determine numerically. Yeah?
I have a very nice question here. So you mentioned the Catani-Seymour subtraction scheme a bit earlier. So for the soft and collinear divergences, we can usually use this technique without any problems. But when we have, say, for example, large Sudakov logs, and we need to resum, can the Catani-Seymour approach be used as it is, or?
Well, the Catani-Seymour regularization is just giving you a way to get to have a local subtraction of all soft and collinear singularities at next to leading order. This is all you can do, and then you can take it because you have certain building blocks which subtract all the soft and collinear singularities from your real emissions locally, and then you can put it into some Monte Carlo and you integrate it in your Monte Carlo event generator, and you can do the same for the virtual correction. You just subtract, and things are finite. This is not allowing you to do any resummation to all orders. Of course, we know that the structure of infrared singularities exponentiates to all orders, and so if you're looking at the structure, at the infrared singularity structure of amplitudes within the framework of the Catani-Seymour dipole operator, then you can see how that iterates to higher and higher orders, and you can use that to extract knowledge about the infrared structure, for instance, of amplitudes at higher orders, and this is being done.
Right.
But in order to actually do a resummation for a cross-section, you have to add more machinery to it then.
Yeah. Thanks.
resum to exponential, and then the ultraviolet also can be shown to resum to exponential.
The what?
The ultraviolet singularities also can be shown.
Ultraviolet singularities typically we don't exponentiate them, so they.
But if one writes as a Borel sum,
We can. Okay, we can do analysis like this. We can look at the renormland structure, things like that. But typically, yeah, how should I say that there is no intuitive or easy way similar to the infrared singularities, because those infrared singularities they can be traced to emission of a massless particle, and then whenever you have emission of another massless particle, you basically iterate and you resum them to all orders. Whereas if you add now, like if you have an ultraviolet divergence, you have some loop, you add another loop, another loop, then beyond the simple renormalon resummations, when you have bubble chains, this is more difficult, more tedious, and not so straightforward. Yeah.
and this infrared singularities, when you have the exponential factor, then can it be related to some quantities like?
Well, basically, so I haven't really talked about resummation yet. So the way to illustrate this now is basically what I've written down here for this example of the cross section of the Dijkstraat cross section in Sturm and Weinberg, because now if you go to the next order, so we have now looked at the next to leading order, you can go now to the next to leading order corrections in QCD, and they've been studied 10 years ago. So if you think of Sturm and Weinberg coming up with this in 79, doing the analog calculation, it took about 30 years or so that people had some interest in the analog QCD corrections, and namely coming from the side of understanding how to organize the resummation there. Yeah, because this is a more challenging example because you have these cones and you have energy fractions. So within the framework of soft collinear effective theory, this was accomplished, and the full NNLO result is known. I just copied the relevant pieces for the leading logarithms from that result. So we have at NLO, we have this CF times minus 8 log delta log beta minus 6 log delta. And now if you exponentiate this, then basically you need to square this thing here and divide it by 2. And so if we square minus 8, we get 64. We divide it by 2, we get 34, 2. So this is correct. Then we have 8 times 6 times 2, we have 48 times 2 divided by 2, so this is giving us 48. So this is basically those two terms here. And then what we also can predict already for the leading log, we have effect of the running of alpha s proportional to the beta function, and that basically multiplies those logarithms here with a beta function and another logarithm in delta. So we have a log of beta and delta coming from this term here. So this is then directly what we can predict based on the fact that this exponentiates. Now, if you want to, coming back to your question, if you want to derive this or set up a formalism that actually does this systematically, then you have to carefully consider your observable. This is then dependent on the observable that you are looking at. For instance, here, Dijkstraat cross-section, or you look, I don't know, at Higgs cross-section in gluon-gluon fusion. You have then to look at, you have to define your kinematics, since this always requires you to be inclusive at a certain level, so that you only are taking, say, soft emission effects and nothing else. So you would have to integrate out already angles and things like that. So you have to be inclusive, but then you can set up formula for effective cross-sections that then generate you this structure to all orders in perturbation theory at a given logarithmic accuracy. So this is then possible, but this is going in a different direction. And I should also mention there are local experts here in this area of research. So can also direct any questions offline to Ravindran. Okay, good. Right, so this was about historical jet definitions. So the modern jet definitions, and I think you will hear more about this in subsequent lectures, so I can be brief about this. They come in two classes. So one is basically a bottom-up approach, and this is what is actually now generally done. So you start from all the particles that you have in your event, or that pass a certain cut in the experiment, or that we put in as particles in your theory computation, and then we choose a distance measure for our particles, like to say how far are they separate in phase space. And for E plus E minus, this is relatively easy. You can take this y-cut parameter, but if you're working at a hadron collider where you have boost invariance, then typically you have to define your metric in terms of rapidity and azimuthal angle, and then you define some cone for your jet, so of radius r. You define your radius r in terms of separation in rapidity and azimuthal angle. So this is then the more general approach that of a jet cone definition that is being used in Hadron Collider. And this is also being this way of clustering particles from in a bottom-up approach together. This is also what is being implemented now in several algorithms which are being used. And at the LHC, we predominantly have the KT and the anti-KT algorithms, which are doing this in an efficient way, putting together particles with a distance measure so that you have an infrared safe and reasonable way of mapping your parton level picture to a hadron level picture. Yeah? And infrared safe is also important because you would want to have algorithms, and this was one of the pitfalls of earlier algorithms. You would want to have algorithms which are also infrared safe in QCD beyond and next to leading order, because some of the early algorithms, the cone algorithms that were implemented in terms of rapidity at the tevatron, that suddenly created you another hard jet when there was a soft seed gluon somewhere in rapidity. And of course, this is nothing that you would want to have, because this basically spoils the whole jet definition. And then depending on the jet algorithm that you are using and depending on the cone size, as a function of rapidity and azimuthal angle, you have then different catchment areas of your jets. They're illustrated here, colored with these colors. So this is the KT algorithm, this is the anti-KT algorithm, and these were other cone algorithms here, Cambridge, Aachen, Ciscone. And you see this is why anti-KT is mostly used nowadays in the experiments, because this gives you nice catchment areas in the kinematic plane of rapidity and azimuthal angle. And uses of hadronic jets are multiple. They come with large statistics, even if you have high PT cuts, and experiments are happily using them for experimental calibration. So you have to calibrate your hadronic calorimeter somehow. You have to measure whether it's uniform. You have to establish missing ET. But then as far as physics outcome is concerned, you can use it for PDF determinations. You can use it to constrain your gluon jets. You can look for quark substructure, angular correlations. You can look for alpha S determinations. So there are many nice things you can do with jets, and I'm sure that you'll hear more about this in the jet lecture. So brings me to the end. I was starting to explain you a few concepts for QCD at work, and today we basically covered infrared safety from different viewpoints, and I gave you a glimpse of how we can understand resummation when we have large logarithms somewhere near threshold. In this case that we've discovered, it was the the dijet, the three-jet versus dijet case, and that radiative corrections are important. And I gave you a short introduction to jets. That's all. Thank you very much. Questions, comments, more questions?
So the KT and anti-KT algorithm, I mean, why the jet structure is so like blur in the KT algorithm?
I don't have the definition on the slides, but it's basically the way. I mean, you look at the transverse momentum differences of neighboring particles when you either cluster them or you don't cluster them, and then you weight them by the relative KT and the anti-KT. You further suppress them if they are further away, and this gives you nicer spherical shapes in rapidity and in azimuthal angle.
So is it always true with irrespective of any process or?
It is so. I think it's largely true that anti-KT gives you better confined catchment areas. So this is why it's being predominantly used. Yeah.
It has also to do with Euler subtraction.
All right. Yeah. So.
If you have circular areas, it's easier to do the jet calibration while subtracting something called pile-up subtraction, where if you have irregular jet shapes in the eta phi plane, you don't know where the area of a particular jet is. You just can't do pile-up subtraction easily. So, and also like KT is more susceptible to pile-up, like for soft radiations.
I have another question. Like, so in one slide you are showing that some F2 and F3, like 3 jet events and 2 jet events. How do I know that what is the sufficient Y value below which I mean we should not consider the soft or collinear as a jet?
So basically, you have to make up your mind. You know, I mean, if you want to have if you want to have an infrared safe quantity here, I mean, you can basically go to large Y-cut. Now you do your calculation for large Y-cut, and you give it to your experimental friends, and then they tell you, oh look, this is fine, but we don't have any rate anymore for this choice of parameters. Yeah. So in order for your prediction to be sensible, it should be infrared safe somehow, but it should also allow for large enough cross-section to be measured experimentally. Yeah? And so this is why now, so at the LHC now when we define jets with a certain cone, R, the measurements are actually taken for different cone sizes. Yeah? And then you have to understand if you have jets with a narrow cone and if you have jets with a larger cone, of course cross sections differ, because in one case you have you only have a small amount of radiation that you put inside a cone, and everything else is outside. And if you have large cones, you basically gather everything in one jet, largely speaking, or in two jets, yeah, back to back if there are two jets with very large cones. So they are giving you different rates for the cross sections. And then the question is it sensible for, does it match for what the experimentalists measure? Yeah. It also depends a bit on what kind of observable you're looking at. Yeah. So for instance, if you're interested in jet substructure, then you would like to have a wider jet, because if you have a pencil-like jet, you know, there's nothing else to look inside for. Yeah.
Okay, thanks.
Yeah?
So I have one.
Yes. Tell me.
So can you show this E plus E minus 2 QQ bar G cross section? This the real
one.
emission cross section.
This one.
In terms of poles.
This one?
No, having 1 by epsilon square pole and 1 by epsilon pole. So actually I have a question with the two parts, in the sense that can we separate this collinear divergence and the soft divergence from here?
So if you know where they come from, then you know one power of epsilon is soft and one power of epsilon is
What is the coefficient?
collinear. If you do the same computation here, which I haven't done, but if you do the same computation here with massive quarks, coming back to that comment, then you will see that the singularity structure is different, because then you will still have a soft singularity, so there will be one of epsilon pole, but then the collinear singularity will be screened by the heavy quark mass, and instead you will have a logarithm of the heavy quark mass, and this would be one unique way of separating soft and collinear singularities.
I see. And the other point is this cross section, and if you look at this two jet event cross section that you have written, that contain log delta and log some other log.
Right.
Log beta.
Delta and log beta, yeah.
So if can we match these two? Like if I try to equate, I want to map log into epsilon. Can I do that or?
In principle, you can. I mean, you have here 8 and 6, so you remember the numbers.
-8.
And then you go back to what we had here. So here we had 2 and 3. So so 6 is 2 times 3, and 8 is 2 times 2 times 2. So there is. I mean, the numbers 8 and 6 there don't appear randomly, yeah?
Yeah, I see.
This is what I wanted to say. Okay, so I think the time is up. Then let me just flash to you the... So basically, in case you haven't had enough from this process, you just go through the various steps. You look at the Born cross-section, you look at the real emission diagrams, you basically square the amplitude, you just do the math yourself. So I've given you some guidelines. I've also given you parameterization of the phase space that you can look at. And you can go through this with pencil and paper. But some advice that I would have is if you want to do this more than once, it's not good to do it with pencil and paper. It's good to automatize it as much as possible. And so there are various ways to automatize this. And I have coded up this in a small script in form, in the computer algebra system form. You can download, this is open source, you can download form from that website. And in the Indico there should also be a small form script which is available for you, and you can simply run it. And then it does the whole computation for you, so this would then be the output. And you would simply be computing the matrix elements that we've discussed by yourself, running this or going through the input and then seeing that you have the 1 over epsilon squared divergence here, the 1 over epsilon divergence here, and then the finite parts with the splitting functions. So you can just do it yourself, not on the back of an envelope, but at the click of a button. That's all for today. Thank you.